Yo! What's up, everybody? Welcome back. Today, we are working on our image classifier for barcodes. When I say classifier, what I actually mean is we are on our way to trying to train a neural network from scratch to identify bars in a barcode. We do this because I want to uh, scan things as I put them in my fridge so that as I use them, I have like an approximate idea of how many grams of milk I have in the fridge so that I can like filter recipes based off of, what I can make with the ingredients I have and also like generate shopping lists and stuff like that. And so my thought is go to the grocery store, I come back, I open the bag, and as I put stuff in the fridge, I just go like boop, boop, boop with my phone, right? Now, it turns out that some barcodes are not dead simple. People in YouTube comments maybe get a little bit mad about this. They say, "Sir, you can just do a 1D scan." But there's stuff like this where I think that the naive approach to this thing is worse than using all of the information you have to leverage to like figure out like the actual width of the bars, right? You can do better on like blurry stuff. You could do better on like occluded stuff. You could do better on like shiny stuff, and like crinkled stuff and warped stuff and all that, right? We can like leverage extra information. So the idea is that like maybe we can train a neural network to learn all these things for us. So we are in the process of building a neural network framework from scratch because obviously you're not allowed to use code that you don't understand, right? So if we have to build it from scratch, we have to understand it, kind of, maybe. And so we have been kind of working towards the past few days, taking a set, we've like generated some like barcode-esque data, right? We've got some Perlin noise, some blur, some like a little bit of augmentation, not that much, and like a line that points the direction where this thing is going. We're kind of hoping that we could train a neural network to predict this red line and get, something relatively okay, right? So we, over the past couple days, have been implementing, adding convolutions to our like GPU execution stuff. So the idea here is you have like a input image. He's got like 3 channels, red, green, blue. Before you say you do grayscale, this is just like an easier way to illustrate the idea. You might have like 1,000 of these at once because we're running on the GPU, so we're doing a lot of things at a time. And the way convolutional neural networks works, or just like convolutions in general, is you take like a box, you take like a little cube, a 3x3 cube, let's say, and you run it over this picture. And by run it over, I mean like this, there's kind of like red stuff at the front here, green stuff in the middle, blue stuff here, right? We're kind of like matching the dimensions of the input here. And we're saying like, put this box on top, put it here, and at this pixel position in the center, you are going to put like a number at the output that is some combination of multiply adds of all of the numbers in the box with all of the like pixels that they overlap, right? So you can imagine that if you wanted to blur all the red pixels, you would throw a bunch of ones in the red box to say like evenly sample from everyone around me. And then you could like put like zeros in the boxes behind, right? And they would say, don't take any of those. You can do kind of like crazy shit with this, but I always show the image kernel Wikipedia page. So just like some ideas here. You can do you can do edge detection, you can do sharpening, you can do blurring, you can kind of do like blurs that are weighted towards the center. I don't know what unsharp is based on a Gaussian blur, so sharpening but like Gaussian style, and you can build up all sorts of like complicated actions from these things. The idea of a convolutional neural network is that you don't really know what numbers you want to put in this box. You're kind of saying like, hey, neural network training framework, I'm going to show you a bunch of examples of things that I think are like correct, and you figure out what numbers to put in the boxes to make that happen. And so like what they'll typically do is you'll see pictures that look like maybe something like this, YOLO V1 paper. You'll see pictures that look kind of like this, right? So the idea here is that you like start with some input and you run like a bunch of these boxes over, and they kind of say like, okay, like start with like 64 boxes, then make 100 or 64 boxes, then 192 boxes that look at the output of those 64 boxes, then like 128, 256, 256, 512. Basically, like you stack these actions on top of each other, and at each layer, every time you run like a new box, the box is like learning higher level information, right? So like, your first step can only look at pixels, red, green, blue pixels, but your second step can look at like, maybe your first step generates like vectors, right? And then your second step can look at those vectors and use those to build up like higher level concepts, is kind of the idea. That's kind of the idea. And so we want to train something that will learn, again, orientation of this. So my thought is that if I were to try to do this by hand, I would run a horizontal edge detection or a horizontal gradient kernel, which basically says like, it kind of looks like this. You have on the left -1, -1, -1, 0, 0, 0 in the middle, +1, +1, +1, and this is kind of saying like, hey, if like going left to right, the signal looks kind of like this, my output signal will look kind of like this, right? Basically, like if there's a big difference between the left and the right, then I'll show that. But if it's flat, then the -1s and +1s will like cancel each other out, type shit, right? So I would do, and what this will do is this will show me all the horizontal lines. You could do a vertical one as well. Add up the outputs of the images of all of the horizontal and vertical, and then like normalize them, right? So my idea here is that I want an output that looks kind of like an output vector of like which way we're pointing, which is like an X and a Y. And I want this to be in the range of like with length of 1. Hand wavy, that's what I'm looking for. And so yeah, if I were to do this, I could do this with a couple convolutions and a little bit of like intelligent math. So we're going to try to work our way up to there, and hopefully a neural network will be able to learn the same thing with very few convolutions. That's what we're hoping. I think the first thing we have to do, though, is we have to set up any training loop, so something where we feed images in and get images out, maybe, or like answers out in some way. We haven't really done that yet. Our only network that we've trained so far is one that takes in two numbers, A and B, and predicts which one is bigger. Right? So he outputs 1.0 of A is bigger and 0.0 of B is bigger. We need to like adapt this into something that actually looks at like pictures. Then I think trying to just train an edge detection kernel, so we can say like, we can just run a kernel over that we want to be the right answer, and then try to make sure that like back propagation is working to the point where like the neural network will go, oh shit, I have to adjust my weights to match that. And then while we're here, we can probably try to set up like some visualizations of some form that run during training, then do barcode orientation detection, and then hopefully we're kind of chilling. Hopefully. All right, a long intro, but lots of context to build up. So let's hope for the best here. So I think we have main zig. What are we doing in here right now? I think we have kind of a visualization that pops up of some training data, as well as a thing that is training this A greater than B neural network. So we kind of have like the pieces in place. They're just not really like stitched together correctly. So this guy, what does he do? He sets up some layers. So he sets up right now like a fully connected 2x1 layer to show, 2 inputs, 1 output for the A or B bigger question. We need to change this to do some sort of convolution. So our layer generator must need like a conv layer, I guess. And I don't really know what's in here, but I'm sure we'll find out. We probably want some sort of, convolutional layer in here. And what did the old version of this guy did? We had like an execute function that basically ran a matrix multiplication for this thing. So what are we running? We're just running a convolution. So here we're gonna have like kernel in here. And when we initialize this thing, we are going to say probably like the dimensions of our kernel. So we're gonna want like in channels, out channels, width, and height. And I guess we should probably do these in the order that we use them. So width, height, in channel, out channel. So this says like, I am going to take a kernel that is, 5 wide, i.e. I can look at things 2 to the left and 2 to the right of me, 3 tall, 1 above, 1 below, and I can do this on like, 3 channels, red, green, blue, maybe. So that's the input channels. And then we are going to create like times 50 of these things to make 50 output channels, right? So that brings us from a red, green, blue image to a 50 by something. And we're gonna, yeah, that's what this guy is storing here. That's what he's storing. So what's going on here? Before we were initializing our weights to 0, that makes sense. Can we like define our dimensions here? This is like kind of like a shitty API, but we can make it work. Width times height times in C times out C here is, we're going to like initialize all our weights to 0. I think you're supposed to like randomize these things so that we have somewhere to start, but like 0's fine. We'll make it work. We'll make it work. And so now we are creating a thing from these initial weights. We're making a kernel here that has dimensions, width, height, in channels, out channels, like this. And I guess we don't actually have to do this. If they're all 0, your backprop will be ass. Yeah, that makes sense. I think we can do this. Create tensor filled. I guess we have like a random number thing on GPU now, so we could do that if we wanted to. But this will be fine for now. So I think we have create tensor filled, which allows us to take a value in here. So we should be able to do something like this. And then when we execute this thing, what are we doing? We are doing a conv many on input with self kernel. And that's kind of it. Do we do sigmoid on the output? We probably are supposed to, but for now, let's not. So we just kind of do this. Okay. If all weights are equal, backprop makes them all move in the same direction. No, because that depends on how they are, what they look at in the image, no? I guess they all touch every pixel though, which is kind of confusing. Yeah, so we might have to randomize them. We'll keep that in our mind for a second. But we'll figure it out. Okay, so this guy's got like a GPU executor, and then width, height, in channel, out channel. And this comes in here. Okay. So let's do, for us, let's make a quick little convolutional layer who is a 3x3 kernel, 1 input channel, 1 output channel. We'll start simple. He doesn't like this for some reason. Why? Expected 4 arguments. Oh yeah, this scratch is gone. Okay. Our optimizer needs to like have this kernel. So I guess here we just say layer kernel. Register these as things that you want to optimize. Cool. And then our training loop. Surely we got to do something. Surely. So what were we doing before? We were generating a bunch of random numbers. And we were then executing the layer. Then looking at the results, comparing them with some expected, calculating a loss, and then doing backpropagation on that loss. Okay. So I guess we should just be able to generate an image here. So I guess like we're gonna generate from our like image generator thing. We're gonna call barcode gen make bars. Okay. And we have some rand params here, so I think we just pass those in, rand params. Some ranges and shit. Our dimensions here, I guess we should match these dimensions. Barcode dims 64 by 64. I guess we'll just say here barcode width, barcode size here is 64. And then we can use this here and here because, you know, we're going to be wanting to generate different amounts of them. So here we're trying to add, you know, maybe like barcode size by barcode size, and maybe like one channel. I think that this thing has to be actually of the shape, like it has to be a 3-dimensional thing. So let's start with like 10 images at a time, right? Because I don't really know how much GPU compute the like backup propagation and stuff is going to take. So we can say that this is our batch. We have some shit, and we probably want to do like reshape this thing. So we'd probably want to do like well, we need to like put these in our. So as how the way we do back propagation is we kind of like build up. For every like mathematical operation we do, we add this to like a graph of like stuff, right? So, you know, we do like, you know, something like this, where you have like this and you have like some output loss at the end. And we kind of like walk this tree backwards to figure out how like any change to any of the things that we care about impact this loss. The way like PyTorch does this is the gradients are just kind of like part of the thing. We have kind of like an external graph that is like tracked separately from the numbers themselves. So we need to like register this batch with that thing. So we have this thing that can take like an arbitrary OpenCL thing and add it to the graph. So we should be able to be like add batch as, you know, initialized. So this is going to be like batch CL, and then we'll say like traced batch like this. Okay. So this is kind of like a we did this stuff externally. So consider this like an initial input to your thing. This is some like OpenGL Windows stuff, so we don't really care about that. And where is our like random source in here? We need to pass this in here. Something like this. Okay, so now we should be able to call layer execute on the traced batch. But this thing has to be reshaped. So can we do math executor reshape this guy? So we take in here batch CL, and we just want to add in the channel dimension here. Num images is 10, and then we could put that num images here and here. Okay, cool. So now we should be able to run this thing through the layer, and this should give us an output, which means that we should be able to like calculate loss from this thing. So what is the like correct answer here? I guess it's like we take our correct answer. I guess we have like a correct kernel. So we have like, you know, desired kernel or something for now, right? We're trying to train one convolutional layer. And so we can just say we have like a thing we expect you to output. I think that's fair. So we should be able to be like, math executor create tensor untracked or something. And we should be able to be like, the initial data, he's attached to some allocator. He's got the data of -1, -1, -1, 0, 0, 0, +1, +1. So we're trying to train like a edge gradient kernel. AI is not equal to ML. Yeah, I know. But it's close enough that, you know, it's an easier title. If I write ML in the title, I think it's like less likely that people will like really understand what I mean. Where anybody who knows that AI is not ML will like get it, even though it's wrong. You know what I mean? It's like it sucks that you have to make that trade sometimes. But it is what it is. It is what it is. Okay, so we just run that thing on this thing. So we have like a conv many here who looks at CL alloc, and he takes in the input, which is our batch. Batch CL 3D, we'll call this batch CL 4D. This guy wants the 4D input. And then when we run our conv many, we want to run this on the 4-dimensional thing. With our desired kernel. Right? So now we can inject the correct answer into the trace graph, and then do like mean squared error loss or something here, I think. So we can just say traced correct here. We append node of correct, and we say this guy just came from nowhere. Don't fucking worry about it. And so we should be able to be like, loss is like tracing executor squared error. Seems kind of right. Of traced batch with traced correct. And that might just kind of fucking work. We probably want to like log the loss, or at least. So can we like loss CPU? We're gonna do something like 2 CPU loss here. Does he need like an allocator and shit? Yeah, he does. Something like this. Is this Zig? Yeah. Yeah, it is. And then let's just do like a sum on CPU for now. This might be like fucking stupid, but you can't stop me. We'll see if this is like really fucking slow. Who knows? I don't really know how many numbers this is doing, to be honest. And then can we log loss here? Loss is this. So something that we do here is we never actually turn the loss into a single number on GPU, because like what you're gonna have is you're gonna have like a picture full of like incorrectness values for each pixel. And then you are going to like sum these together to create one loss number, right? And then when you do backpropagation, we're literally just gonna undo this back to this. So it's like we can just start backpropagation here. You know, we don't need this number on GPU. So that's why like this loss is, this squared error thing doesn't sum, because it's like, why we don't need to do that work. But it means that if we want the number ourselves, like we're summing on CPU for now. We probably could sum on GPU. We spent a whole bunch of time looking at parallel sum, and it was like not worth it, basically. Shockingly. You would think it would be easy. But get fucked, I guess. Okay, so we run our backpropagation, and then we optimize this thing based off of the gradients. This thing is not normalized to like batch size, so we might have to adjust the learning rates here. But let's just kind of do this for now and see what happens. Why are results here not being used? That seems bad, no? Because we're not looking at the results here. We're looking at the traced batch here. So, okay. I mean, that looks like a maybe. I'm not like 100% sure this is wrong. What's this guy pissed about? No fields, remember, create tensor field in tracing executor. Right, so our tracing executor here kind of wraps a lot of APIs of the normal executor. And so we just kind of have to like implement the ones that we're missing. Create tensor field. This guy takes in a value here. All right, what's next? When I need to classify photos, I use Google Cloud Service, and for classifying other objects like UI elements, I use a perceptual differing algorithm. Yeah, but what? That's no fun. That's no fun. Asking some server somewhere to do stuff with stuff they know, that's cheating. We don't cheat around here. We only run code that we created ourselves from scratch. Otherwise, it's cheating. No field named kernel and fully connected. Yeah, are we fucking mental? Did I just try to return a fully connected when I wanted conv? Yeah, oh, here we go. Conv. Bum ba bum 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 bum. Bum ba bum bum bum. Alright, what's here? What's he pissed about? Oh yeah, we did just forget the dims, huh? This is 3x3. And this needs to be by 1 for this to be able to be applied to the conv later. Why Zig? It's just the language I'm most, happy using right now. If you're asking, should I use Zig for machine learning? The answer is probably no. But, it's as good as C. Better than C, at least. This is just the wrong fucking thing. So the output of make bars here is actually, like, he's got other shit in here. So we want to use bars images here. This guy needs to be tried so that the error is unwrapped. Conv many does not exist in tracing executor. So true right now. So we can just implement that. So can we just huck a little conv many here? What is he gonna call? Conv many here. What does this guy take? He takes in a tensor and a kernel. So here we've taken kernel here, and we apply the kernel here, and we register this thing with our execution graph, which means that this is actually going to be a conv with probably like A is the input and B is the kernel, probably. Probably. You can use libtorch or whatever, though. Also, if there is one, that's not the point, haha. Yeah, exactly. Okay, what's going on here? Found, oh, we need self get the underlying tensor. So this is kind of like, we have like a tensor type that's kind of like backed by different resources. So in this case, like the tensors that come in are backed by like node IDs in our execution graph, and we need to convert them into like actual tensors that the underlying thing can use. What's this guy want? He wants A and B. So this is in buff. We want node IDs here, so we throw the buffer field at it. And now are we chilling? Probably forgot to write try again here. Everything needs to be tried. Every failure needs to get propagated. And here we need to handle backpropagation of convolutions now. So looks like we can do something like backprop 2 params, and we use conv many grad here as the output. Is everything else fine? I think so. Okay. So good news, it compiled. Bad news, we segfaulted. But it's part of life. Let's take a little peek. What are we fucking doing stupid? That's not good. I wonder if we're like feeding invalid memory from our like graph. Is this in make bars? That's surprising. Are we doing something stupid like we're barcode generator? Does he take in? He takes in like a CL allocator that he holds, and then maybe we're like resetting the allocator in some way that we're not supposed to. No, shouldn't be, because we checkpoint we don't reset the allocator to here. Where is this checkpoint taken? Oh yeah, this just shouldn't be here. These checkpoints need to be taken like as close to the loop start as we can. All right, that's probably better. Okay. So bad news, loss is going up to infinity. Good news is that it is running. So I guess the question is why is the loss growing? It could be too high of a learning rate. It could be that the gradients that we're getting are not correct. And it could be that our initialization of them to all 0 is fucking everything up. So we already suspect that as a problem. So can we just not do that? I think there is a rand function that we can use somewhere. Math executor function rand. Okay, and then is this on the tracing executor? Yes. So we should just be able to call, like, instead of create tensor filled, can we just call rand? Just fucking, like, do whatever the fuck you want here, bro. Expected 3 arguments, what are they? Oh, rand source, of course. Are you doing gradient ascent? I shouldn't be, right? Because we're using the same optimizer that we used in the past. So I would be surprised if we managed to do gradient ascent again, but it is possible. Okay. Okay, let's take a look. That loss is still growing like crazy. So I guess what we should do now is maybe take a peek at the gradients that are coming out and make sure that they look like somewhat sane. Somewhat sane? So also, let's like reduce learning rate by an order of like 3 magnitudes because, okay, wait. Just dropping the loss there, or the learning rate, does seem like it's helpful. At the very least, the loss isn't exploding anymore. It's not great, but it's not exploding. So, can we also look at the kernel that's coming out? We want to see how close is the current. What is the current learning rate? 0.0000001. But it's because like the, you know how I said we don't like, we're not like normalizing the loss. So this is kind of like applying to like every single kernel weight. The like loss is of what? It's over like pixels in the input image set, right? So if we are like taking how much any change in any kernel weight would affect like the sum of all pixels, which I think might just be like a really big number, right? So maybe we should be like normalizing our learning rate according to like batch size, where it's like number of things in the output. You know what I mean? Like maybe we should be normalizing to the batch shape. The log, like, you know, our loss here, like what is our I think we have like loss num dims num elms here. Loss number. Yeah, so we're like we're like applying this to like unnormalized 40,000 things, and so maybe that's causing problems. I also want to see after every iteration right now, can we just print out like what the kernel is? const learned kernel CPU. This is going to be like tracing executor to CPU using a heap allocator and a OpenCL allocator, and we want the tensor for the weights, which is in layer kernel. Can we just like print this thing? Learned kernel. Let's see if this thing's getting like at all close. That'd be kind of interesting. Uh-oh. Okay. Learned kernel. Positive, negative, positive. It's not looking good. It's not looking good. But maybe he needs more time. Maybe the batch size needs to increase. Who knows? Who knows? Let's take a little peek here. So I want to see, at the current shit, how much GPU are we using? 10 images per batch is pretty small, I assume. 10 64 by 64 images. So I just want to make sure that like we're kind of like working our way up a little bit reasonably. Yeah, this is like, hold on. Is this broken now on my newer card? It might be, huh? So I just, oh no, wait, I've had this, no. I didn't change my card. I did a CPU, or like a computer upgrade recently, but it was all, CPU and motherboard. So this shouldn't matter. But I guess we just YOLO it and hope that I can like kill something that's behaving really poorly. Okay, is the loss going down? That's the question we want to ask ourselves. 346,000. 179,000. 145,000? Wait, maybe? 110,000? 116,000? Does this kernel, is this starting to look kind of right? We got... No. But the loss is still going down, so that's a good sign. Maybe our learning rate is too low now. Maybe this is just taking, maybe this is just a thing that takes some time. But this thing is definitely trending down, which is good. By some metric. Negative, negative, positive. These guys in the middle, we kind of want these guys to trend towards 0. So we're not looking too good yet. Okay, let's try, I mean, this thing can clearly do more, right? Like, each batch is running very quickly. Ooh. Ooming here, though, on CPU side, so let's just kind of like bump up our allocator sizes. I assume it's this one. Okay, that's interesting. Sometimes we're getting unstable. Land BPS, thank you for the prime. Okay, what we really need is a way for this thing to be easier for my brain to process, right? So can we just add the loss to like the GUI in some way? Let's just do that so that I don't have to fucking keep doing this. I guess we're kind of like on here now, huh? Sometime before now, we started trying to train edge detection kernel. So what do we want to see here? We probably want to see every once in a while. Let's just start with the loss. So somewhere we have like GUI widget factory here. This guy we have, he just sits on an image view. So let's start by making like a layout of some form. So this is, layout. This guy goes in here now. And here we have like layout at push widget here. Yep. Let's do something like make Oh, we need to push whatever the fuck we were doing before. So this is the image view. Has to go in here. I guess like this is for later though, because this thing isn't really showing us anything useful yet. Can we do, maybe just do, make text box, make label here, and this guy's gonna come from the like loss label here, and we need to like make something that displays that. So I think we can do this. Loss label retriever. This guy's job is to like take the current loss and turn him into like a string of text that we can put in the GUI. So I think we have like function as text here, get text I think, who is supposed to return a slice of something from himself, if I remember correctly. So here we'll have like loss as a floating point number, right? And we will also have like a buffer to like serialize the loss into. So maybe something like, 20 bytes is probably good enough. Buff print into self buff of this out of, I guess it's just a number. And this will be like loss, which means that 20 bytes is like way too much, but like whatever. Whatever, I don't really care right now. Something like this. By the way, he also implemented his own GUI framework. Yeah. This is going to be like a nice little test for it. Loss label is a loss. Oh, this guy actually, I think this needs to be a pointer. I think, because like the way this shit gets copied around. Sum here. Loss sum is 0. And then here, we just allow loss sum to be like this. And now hopefully our GUI shows that shit. This needs to be like this. Loss label retriever. I'm not quite happy with the way this like retriever API works. There's like a little bit of a problem in there with like some pointer shit, but my dumbass forgot to dereference the float pointer. It's crazy that it allowed me to format that like a number. It's pretty funny. Okay, so we can definitely see a number here. I'm not really too happy with that number. It's going the wrong way. Yeah, why is it going up? That seems bad. Was it going up this whole time? When it was at 50, was it? Oh, wait, we're not zeroing it out. I'm a dumbass. We need to still do loss sum is equal to 0 every iteration here. Otherwise, we're just like summing the total loss of all runs ever. There we go. There's a number. And we can kind of see it like going down a little bit sometimes. Cool. Now I guess we just like crank up. I'm scared to go like too fast on increasing the number of images because like when it goes bad, it goes like really bad. My whole fucking GPU just like stops working. We pre-allocate everything here, so let's just bump these numbers. I don't really fucking care for using like 100 megs of memory up front. I don't give a fuck. Okay, here we go. Computer still looks like it's working, but now the batch sizes are like looking a little bit more reasonable. We're at least like spending time in each batch. This number is in fact seems to be decreasing. Are we still printing the kernel? We are, and it's pretty incorrect. So what would be maybe interesting is to show the correct answer as well as what we are getting. And then maybe like a way to change the learning rate on the fly here would be kind of nice. right? So that we can experiment with like how different learning rates affect this thing. The fact that the GUI runs in the same thread here though is a little bit of a pain in the ass. But we'll live. Okay, so let's do that. Where are we doing our other like layout stuff? Can we do let's add a widget that's like make drag float. And this guy is just going to be based off of like learning rate probably. This is going to be like really hard to work with. I don't know if it's going to support us doing numbers this low. So maybe we'll call this LR multiplier. LR power? Yeah, maybe we do this. So we'll do like LR power, which will let us kind of what is it predicting now? Edge detect image? That's what it's supposed to be doing. Yeah, maybe let's render the correct answer, actually. I kind of like that better. So can we do something like, okay, these image views, they try to fill up like the remaining space, if I remember correctly, or maybe they just try to fill width. Let me see. Image view, what does this guy do? His, on update, we just try to take up the entire available size, which is bad. We shouldn't do that, but we can kind of just like dodge this for now by putting it in a box. Rendering output will be helpful too. Yeah. So this guy takes in size of, you know, let's just say like 300, like 300 by 300 is probably fine. And then fill style is don't fucking grow at all, please. And so if we look at this guy now, we should see an image. Okay, so that's kind of like the input image. Now we can try to show the output image as well. So here, I guess we just make like another one of these guys. Jeez. Can we just like duplicate this thing? I guess we just do this. Make image view. I don't know. We'll figure this out. What goes in here? Image view. This guy has a GUI allocator that he wants. He's like, I am going to live in the GUI. Which is a render allocator, I believe. Then I think we have like GUI alloc make a sub allocator because this guy's gonna like ditch some shit every once in a while. So image view or something. Okay, so that's what's gonna live here. These buffers need to be created as well, which we can just do in this function. So our program is going to be shared. But this stuff is going to come like this. Solid color renderer. I think it's like this. Okay, then we need our GUI state as well. Which comes from GUI like this, I think. widget state. Okay. And then we need a scratch allocator, I guess. I guess. We need an OpenCL allocator as well. So many allocators. So many things. I guess maybe these should just like pass these around together or something so that we don't have to like make so many parameters. And then a CL executor as well to like do some OpenCL shit. Jeez Louise. Okay, and then... Oh, actually, I just don't want to do this here. That kind of makes my life easier. Okay. Cool. That makes this easier. Okay, so now we can make an image view by going make image view. This stuff kind of all goes away. And this guy wants like GUI alloc. He wants solid color renderer. He wants... I didn't look actually. He wants GUI state. He wants... That's it. I guess he wants like something like this. This guy is already like this. Okay. So hopefully now we have like a function that we can call to do this a little bit more easily. So now we should be able to like make like a like second image view. So we should be able to be like, this is going to be expected output. View, I guess. And we need to initially set the sample to like a null thing, I guess. Null image or something. And we'll just set its initial orientation to 0, 0, because this is like a thing for later that we're not actually using right now. And then we need to define null image here. So pub const null image is equal to CPU image with data of empty, and width is 0. Okay. So now on every frame, we probably want to set some samples here, right? So we probably want to... I guess here, our expected output, if we're using like the same image all the time, we can kind of just run this shit once. So we probably take like our desired kernel and do something with that. Right, so we probably say like math executor conv many with our allocator. We run this thing on validation set images. Yeah, sure. Sure. And the kernel is desired kernel here. Cool. Expected output. And so now we need to like put this thing in here somehow. So we have like expected output view set sample here with I don't know, tensor to RGBA. I don't know, man. Let's just see if this does what I want. Okay. There's a lot of, like, bullshit in here, but hopefully we're getting close. Expected 5 arguments. 1, 2... yeah, so we're missing index here. Oops. And then also our executor. Did I get this in the right order? No. Oopies! Alright, please God. Okay, that compiles, and so we should see like a horizontal edge detected thing here, but instead, division by 0 here, that makes sense. Yeah, so who's trying to call this thing? On set sample 2GL. So here we need to do like if self data len is equal to 0. If it's not equal to 0, we're allowed to do this. Else we just use like invalid, which I think is a valid texture, if I remember correctly. It's like something like this. There we go. All right, does that stop it? Still not good, huh? 2GL calc height. Oh, it's in here. If self data len is equal to 0, return 0. Invalid dims here at conv many. So we have desired kernel validation set images. Oh. We need to reshape this thing. So it's like math executor, reshape this thing to be I don't know, it's probably like 64 by 64 by 1 by 2 or something. I think it's something like that. Playing type Tetris with those monster signatures, yeah. Get fucked me, I guess. I will say, this is not the best code I've ever seen. Okay, there we go. So, I don't see the expected, probably because we didn't put this anywhere, so we want to put expected output view as widget here, and then hopefully we see the like edge detection output somewhere. Okay, here. Nice. So what you're seeing is kind of like an almost inverted thing, which makes sense, right? Because at the boundaries from dark to light, we're going to see it be bright, and boundaries from light to dark, we're going to see it be really dark. So I think that's chilling. So can we now also add in like the actual output here? I don't really know where this is going to go yet, but is there any like tracking stuff we have to do here? So probably we just at the end of every batch, we run, you know, conv many with the input tensor. So this is going to be validation set reshaped. We're going to run this on with the kernel that is in our layer. Yeah, something like that. But this thing is traced, so we need to do like CL, get CL tensor from this thing. Okay. And then we have the like actual output here. And then we just do whatever we did to set this thing here. With actual output this time. All right, let's see what this does. Nice. Nice. Now we start to see it like fade in here. This is what it's like producing, right? So you can see there are some pieces here that are like, I actually can't tell if this just looks like the input maybe. No, like this is inverted, which is good. Okay, this is kind of fun. So now the question is why are we not learning? I wonder if we should visualize the gradients too. What's the first pick in the GUI? This is the input that's being fed to the kernels. So this is like the input image. This is with the, after we run the correct kernel on it, and this is after we run the learned kernel on it. So like, it's actually like surprisingly close. Like, brightness here is like obviously quite incorrect, but I will say like the at least like stripes are in the right place, right? Like we go from having this like fat white boy in the middle here to having like a fat dark area with like a gray thing in the middle. Fat dark area with gray thing in the middle. Like I think we're actually like surprisingly not that far. Why learn when you have the correct kernel already? Because this is like a way to prove that our backpropagation is working more than it is a way to actually like get the kernel, right? Later we're going to use this to like try to actually train something that we don't have the right answer for. Okay, so interestingly too, you can kind of see like the output's kind of stabilized. So now the question is why the fuck is this not working right? Right? So I would hope, so we could try playing with the learning rate. So here you can see, will mean squared error instead of single squared error help? My understanding, which could be wrong, is that those are the same, right? Like, if I have like a list of numbers minus a list of other numbers, right? And I like calculate like the squared error of each of these guys and then sum them, is that not the same as just calculating the squared sum of all, like the gradients from there? When you do like a sum of like thing, the gradient for how any individual thing applies to like the total is like the same as it is to any individual element, no? Because like adding in, like, you know, if I have like ax plus by equals out, changing x or changing y, or I guess, sorry, let's say out is equal to x plus y, right? Like changing x has a like linear effect on output, and changing y has a linear effect on output. So I feel like doing mean squared error is like you're summing a bunch of stuff and then dividing them by some number. And so by dividing the learning rate, I think I'm doing effectively the same thing. You know what I mean? I think. Okay, so it does seem like maybe a lower learning rate than whatever we were doing is maybe interesting. Like maybe it's like struggling to like overcome some hump. Oh, that's funny. The way that the GUI is set up. Okay, so now it's learning like way too slow. Can we try? Okay. What if we just hucked like way more samples at it? You know? Hucked way more samples at it. And instead of like looking at like the same image every time, I wonder if we were to show like an image from our training set, if that would be kind of helpful in some way. Maybe we're getting outside the realm of like how much stuff we can like reasonably train here. Yeah, this is insane. Each batch here is taking like forever. So yeah, this is like unusable. So I'm kind of on the side of not doing this many samples at once. 1,000 at a time seems pretty reasonable. Yeah, it's interesting that like usually your images and models are larger. It'll be like if it batch size like 32 in VRAM. Yeah, that makes sense. I guess like the question is do I think that this is wrong? Like in reality, this is doing like an okay job. I wonder if I decrease learning rate more, can we also like when we print the learning rate, can we do something like, yeah, let's just try decreasing it further. Learn 10 times slower, but maybe you'll find like a more correct answer. But in reality, I'm not really sure I'm convinced that like the answer it was getting to was like that wrong. It's not like as intense. But like it is kind of like getting like the shapes that we wanted, right? You can see it like started with like something that looked more like the initial image. Yeah, I mean this, we do see like the same patterns here, right? On the corner it's a little fucked up, but like these patterns are about right. Okay. Let's leave this for just a little bit of time and see. Is there a linear network on the other side of the conv right now? Maybe it has a bias or something that we're not seeing because we conv directly. No, there's nothing on the other side. We're literally just like trying, but I think that it's reasonable to be like, hey, I have like a loss for, like I have like a thing that I want you to create a convolution for. Fucking get there, please. Like, that it, like, this is just one of the steps of the final output. It's also possible that like mean squared error is like maybe allowing for like it to get kind of close to the right shape, but maybe it's not like, how do I say this? It's not like penalizing something as much as it should, right? Because of the way that like squared error like spikes for things that are how do I say this? Like far away. But you know what? I think that maybe this is like, I'm like not convinced that this is like wrong. And I'm not really convinced that if I left this for a long time that it wouldn't get better. It's stuck. I don't think that you can like necessarily tell that. I think that like sometimes it looks like things are the exact same for a long time, but like you sometimes see this like behavior where the loss kind of stays flat for a while and then like hits like a cliff. It could also be that like our optimization strategy is kind of poor, right? We're kind of just using, what is it called? Stochastic gradient descent or something, where we're kind of just like moving in the direction of gradients at any time. There are one convolution kernel is linear. No, linear shouldn't get stuck anywhere. I don't know what you mean by linear. But like maybe. Like it's not the same as like a linear layer, right? You have like way less weights than on like a real linear layer. But this number is still going down, by the way. Like a little bit ago, we saw it kind of sitting there at like 100,000 for a little bit or a million, kind of like fixed there. Now we're seeing it around like 800,000. So I wouldn't be surprised if eventually it does get to the right answer. And it's just that like it's easier like to be like again this does resemble the correct answer. So it could just be that like the amount of effort that it needs to get to the real right answer is like hard to overcome, you know? Because like you can see that what he's learned here is he's actually learned like a pretty interesting thing. He's got two negatives here. SDG with momentum instead of raw SDG will make it go faster. Most likely, yeah, I agree. So I think that there's like things to investigate, like like better optimizer, momentum, atom, etc. But this is gonna be like a future thing. I think I'm gonna say that I'm relatively happy with what is coming out here. It's not that wrong, right? It's just event. It just has some work to do. Oh, all three of these guys are negative now. That's good. He's getting closer. And are all three on the bottom positive? 1, 2, 3. He's getting closer. He's getting closer. Look, we're at 60,000. Okay, so I'm gonna like say I'm happy enough with that for now. Happy enough. So, what might be nice now is to try to actually get barcode orientation out of this guy. So, again, if we were to predict this thing ourselves, we would do what? We would take horizontal gradients over the image. And we would take vertical gradients over the image. And we would essentially just try to normalize this, right? So we would like do like sum. And then do like a squared plus b squared square root for length. And then do like this over len and this over len. And this would give us like probably something that's approximately right. Now, this is, we can't learn this. This is not like a function that the neural network, if signs are important, what range are we visualizing? -1 to 1 or 0 to 1? We're clamping anything below -1. So yeah, we aren't seeing everything we're supposed to. You're right. I had that in my head, but I wasn't going to say it explicitly. But you are right. Maybe we should be visualizing the absolute value. But later. Let's first just try to make a network that predicts the orientation and then see how fucked we are. So, what's this guy supposed to do? He's like, so this is not trivially learnable, but I think if we did something like give it like a few convolutional layers to like a few channels it can look at, then like maybe if we created some sort of like nest of like fully connected elements that could approximate, a square root or something, then maybe we could get somewhere where it would like get the right answer. Maybe. So I'm thinking like maybe we start with like, a few kernels at full resolution. Ooh, we don't have any like pooling right now, which means that we have no way to like shrink these things other than just by sampling. So maybe we just say fuck it. We'll do a couple stacks at full resolution just so that like, give them some chance to like learn some things. Maybe even just doing like, four full resolution outputs initially is fine. Can you stride your convolutions maybe? Yeah, we could, but we just don't have that like implemented right now, which I think would be I don't want to go through that work of figuring out how to like backpropagate that right now. Yeah. So I want to see if we can get away without that first. then maybe we do a trick to kind of fold all of this stuff back down into like a couple layers at the end. What if we just like, if it's fine to just go like from here into the rat's nest of fully connected, maybe that's fine. I'm kind of curious to see what that does. So if we want to learn a square root, can we like, I don't really know. Can we just like ask ChatGPT? This seems like the type of shit that he would be good at answering, right? If I'm like, how, like, what, if I'm expecting a neural network to normalize, two numbers, as a 2D vector with length 1, like, how many nodes of fully connected layers should I expect to need, or something? Like, I'm expecting, like, you know, some low number of, you know, like 3 layers of 64 nodes or something, right? Is okay, so he's understanding what I'm asking, which is good. One hidden layer, sure. So he's like, just fucking like one hidden layer, 16 neurons is like maybe good enough. Okay. Okay. So let's do something like where are we registering weights with our optimizer? Here. So let's do like a couple 3x3 kernels. So 1 input channel, maybe 2 output channels initially. Let's just like let it go again. You know, 2x2. And then let's do a few like fully connected things, right? So layer 3, we can do fully connected. This is going to take every pixel in our input. How about your orientation labels? Can the network really tell flip barcodes apart like 180 360? Not yet, but we can just make it so that we calculate the direction based off whichever's closer, right? We can just absolute value the dot product or something like that. Okay, so this guy we're gonna look at like what does this guy want? He wants a scratch allocator. And his inputs, his initial inputs are like very high, right? So this is gonna be, we have 64 by 64 images. So I guess this is 64 by 64 inputs. And then can we just do like to like 16 and then maybe like another 16 to 16 or like 32, 64, I don't know, it doesn't fucking matter. I guess each of these does add a lot of cost at the first layer, so we can just kind of like do something like this. You know, something like this. And then we register all our weights. Something like this. You know? Something like this. And so now we have to like run this thing correctly. So when we are running this thing, it's no longer as simple as just calling execute, but it's more like we take layer 2, execute. So this is from like layer 1 out. Layer 2 out. From 2 to 3. From 3 to 4. This is looking a lot like I shouldn't have to type this over and over again. Are you planning on saving the weights? Yeah, eventually. Um, eventually. Eventually. But for now, we're just getting a feel. Okay. So here, now the correctness is no longer based off of us just doing a convolution. But here, we can look at the orientation of the bars, right? Um, so we need to do something where, like, what we can do here is we can just only generate bars that are pointing the right way, right? So we have, like, rotation range somewhere, I think. When we create this thing, surely somewhere we are generating like a rotation parameter. Surely. Yeah. And so can we just only generate numbers from like negative pi to pi or something? Right? Because then there's no ambiguity, right? I think. So let's think about this. If this can point this way or this way. And so we just say not this one. This can point this way or this way. We say not this one. This can point this way or this way. We say not this one. Yeah, I think we just only do rotations of, or we allow arbitrary rotations, but we heal the orientation here to be times 2. Yeah. If you do 2 times the angle, that's like an easy fix, right? So here you're generating like anything in this range. So if you multiply this by 2, you get this. And if you multiply this by 2, where does that go? No, there's like some trick here. Oh, but fuck it. Um, let's just say only generate things from 0 to pi. And that will make our lives easier. I think that'll make our lives easier. So then it should learn to always point up, basically. Okay, so the correct here is no longer a conv many, but it is just the orientations, I believe. So here we should have like a 2 by num images array here. So we should just be able to get like bars orientations here. And we should just be able to do like squared error between results and bars orientations. I think. Like we should just be able to do this. And then what do we render here? Can we render the, instead of like rendering many images here, can we just render like 2 bars here? So on set sample here, can we just say set predicted? And this guy is going to have, you know, predicted orientation buffer and predicted orientation render source. Yeah, that seems reasonable. And then here we're just like, hey, here's predicted orientation. And he's like, let me update that thing. Yep. And then when he renders, he just renders the, he renders predicted in a different color. maybe in blue. Seems reasonable so far. And then all we have to do is on our image view, here, we say, we want to run this thing. We need to run like this whole nest of shit on the validation image. So it's almost like what we should do is we should like mirror this thing and not trace it. But it's fine. So here we should be able to be like, can we do something that like runs the whole network? I don't know yet. I don't know yet. All right. I'll just copy paste. Fuck it. So now we're no longer showing this like expected output shit. And can we just run this on append node here of validation set orientations? No. Images? Yes. Which reshaped, probably. We need this to be the right shape. And we are saying this guy is a new thing. Okay. And then we take the validation results and we render them. So we say, can we just start by writing them down? To CPU. All right, here we go. Here we go. We're getting somewhere. Let's just start by printing these. Val results. All right. There's now stuff that doesn't need to be here anymore. Oh, wait, what's this about? What the fuck? Oh. Fuck. This is just in another thing that isn't happening right now. Get me out of here. All right. So invalid matrix multiplication here because the input to the layer that is doing a flat fully connected, he's expecting not a 4D input. What is he expecting? He's expecting like a 64 by 64. I guess by 2 probably. So we need to like reshape this to layer 2 out reshaped is try layer tracing executor reshape this guy is now going to be like layer 2 out dims get 0 times layer 2 out dims get 1. Just flatten this motherfucker out. You know? And then we still have many images of these though. So I think that this is okay. Yeah, something like this. Where does reshape take the valid in first? So something like this probably. And then we need to run this, do this for the validation shit as well, right? All right, something like this. Fuck. The fuck? Whoa, what the fuck? All right, let's try that. Invalid dims. 8192 by 16 instead of 8192 by 1000. Really? Where is that 16 coming from? Oh, my bad. It's in the validation set shit. No. 316. This is here. Okay, so like, what am I fucking doing wrong here? 0, 1, 2, 3. So he's expecting... Okay, so 8192 is 64 times 64 times 2, right? Yeah, okay, so this is like correct. But now we only have 16 of these things instead of 1,000, which is very confusing. So we have 3 width, 3 height, 2 input channels, 2 output channels. Then this guy has 16 outputs. Okay. Oh, does this guy not handle, like, many images? What am I looking at here? We're supposed to have 2 dimensions here. Okay, so we have... I need to draw it. So here we have 16 outputs. So we'll draw 3. Each of which is connected to 8,192 inputs. So we're saying each of these 16 outputs is multiplied by every single input. Okay, so that seems reasonable to me. So there are 2 8192s here. I think maybe the order here is incorrect. This guy might want the other order. So we have... Yeah, is this backwards? Because, like, okay. Reducing the numbers, we have a matrix here that's like in 1, into, like, wait 1, wait 2, wait 3. And we're supposed to be like, here's like an input, which is like entire image. Right? So this should be each column here is like sequentially multiplied like this. And so where the fuck, how the fuck did this work before? I guess that's the question, is what the fuck were we doing when we were doing like A times B? So we had a batch. Oh, we had something that was like A, B, A, B, A, B, A, B times a thing that took in like 2 weights. So each sample was like its own column of the matrix or something like that. Yeah, I see. I see. So we have to like somehow like swizzle this shit for this to work. Or we need to implement something better here. Fuck. Yeah, because what we want is like we want like an array, like a we want like image 1, image 2, image 3, which means that we want like top left pixel for each image, kind of like sequential in memory, for this to kind of like work out correctly. Yeah. Which is annoying. Um, what if, yeah, I guess like transpose or something more complex. I think it is just transpose. So I think we can just call it transpose. I'm okay with that. Is this easier than uh just fixing our matrix multiplication to support like many dimensions? Maybe, right? Like fix me and support many in tensors or something. I don't know. I guess this is actually kind of more like it should go on the fully connected layer thing. So it's like expects yeah, matmul expects transposed like funny input dims, I think. But like whatever. Okay. So transpose here, we're gonna have some output thing. So we're gonna want like reversed input dimensions. Oh, this is such a pain in my ass, man. What a pain. What if we cheat it for a second? Does that help us? Oh, fine. We'll transpose. And we'll just say, if in dims len is not equal to return error unimplemented or something. And then we'll say, flip this thing like this. And we will say we need like some transpose kernel. So this guy takes in a in and an out and a width probably. Does that break the gradients? We're just gonna have to do like transpose gradients as well. But that's okay. We can do that. Uh, pretty sure. We can just transpose the gradients on the way back. So in height, I guess, goes in here. Or these are like uints, right? And we probably have like if global ID is greater than or equal to in width times in height, return, we have global ID is get global ID 0. We this thing needs to be a function here, and then it's like out at global ID is equal to input at, I guess we want like our so it's just like our out x, I guess, is global ID percent in height, because we're flipping. Out y is this. And then we are sampling from in Am I stupid? Is it easier to think about this as in terms of... Yeah, no, okay. Out x, out y. In x is equal to out y. Yeah. So we have like input times out x plus out x times in width plus out y. Yes. This is kind of like the flip of this thing, I think. Is that right? So in height is our out width. So this makes sense. Then we usually multiply height times this, but instead we multiply x times width. Yeah, I think that's right. The other way around, no? No, because we're sampling rotated. Right? So we're sampling from our y is their x, I think. We could write a quick little test. Should be pretty straightforward. Okay. Transpose. Pose kernel is equal to transpose kernel. So here we're like, try execute kernel with transpose kernel with in out, you know, something like this. Then it was uint of in dims 0 and 1. Okay. Then this is out is create tensor with indims. Easy. Sorry, out dims. All right. So a little test here. Let's make a, I don't know, just a little 3x2 thing. So here we have like 1, 2, 3, 4, 5, 6. Right, we create this thing, so we have like fixture, math, create, tensor within CPU, and this is going to be 3x2, right? We have out GPU is transpose. Like this, within on the GPU. Okay, we should, we expect that the dims are, you know, out GPU dims 0 are 2 here. Expect equal here. And dimension 1 is 3, because we expect those to flip. Okay. And then the out CPU is, or expected, I guess, is expected to be 1, 4, 2, 5, 3, 6, right? This is kind of the rotation of that thing. And we have out CPU is get this thing on the CPU, please. Okay. And for expected out CPU, expect approximately equal of expected with actual in some, reasonable distance. And let's just see if that does what I expect. Fuck! Here we go. It's initial data, uninitialized. All right. Fuck. Expected 3 arguments. 461. Right, so he used to run this with out buff, out dims, num elms. This is how many times this thing is running. Okay. Wrong pointer type here. Expected needs to be explicitly a list of F32s. And then hopefully we're fucking chilling. All right. Okay, so does this transpose correctly? Yes. Okay, so this is chill. And so now we should be able to... hello, here. We should be able to say... Okay, fuck this validation shit for a second. Can we look at here? Tracing executor transpose. Like this, except tracing executor does not have transpose, so we just have to quickly make it. Right, so this guy kind of calls this shit. And then on backprop, we just have to transpose back. Right, so I think here we need to say we have like transpose has a node ID. And then when we do backpropagation, the weights are just going to be like in the wrong spot according to their input. So we can just do like, I think it's literally just like, what's going on here? So usually what do? We like call the gradients. So we need to say that our new gradients are like a transpose of the input gradients, right? So it's going to be like this? Something like this? Do we like inject those gradients somewhere? It looks like we just get the gradients and shove that shit on, dude. That's what it looks like. So I think that's fine. So now can we train now that that thing has like been transposed? Oh. Wait, what the fuck? Oh, we didn't save. And then here we want transposed here. Fuck. I know you get this question a lot. What's your take on Rust? It's decent. You know, it's not too bad. I think that my kind of value system at this point kind of lines up better with something that's a little bit less, how do I say this? Uh, I want something like a little less rigid, because I like find that like my workflow is very like experimental, right? I want to like try stuff and then see if that works, and then like get the like make something pretty after. Um, and Rust makes that workflow pretty hard. So I'm not the like. I think it's like it might have its place in like real professional settings, but for myself, I'm happy to tank uh some like allowed incorrectness. You know? Okay, why are my dimensions here on squared error not matching up? So my results here are 1,000 by 2, which I guess is probably just wrong. We probably just want to call like results transposed is equal to try tracing executor transpose results and use those down here. So we've got some like dumb shit happening, but that's okay. More invalid dims. Interesting. Did we fuck up our transpose backprop? So this is in executor 551. This downstream, this does not match in this. I mean, what the fuck is going on here? Downstream 2 by 1,000 does not match 1,000 by 2. So that means that this transpose backpropagation must be fucking wrong, right? It's gotta be. Okay. So we are saying did I get like this transpose in here? I'm saying, yo, transpose this thing and say that it came from this. Okay, so can we say std debug print reversed this to this? Um Oh, I'm an idiot. I'm transposing the input. Well, I should be transposing myself. I should be doing this. Downstream gradients. There we go. So I was just like looking at the input and transposing that instead of looking at like the gradients I have and transposing those back. That makes sense. Okay. So that's promising in some way. We are seeing like training happening. Now, are we seeing training go towards anything? Not necessarily. Right? But we're getting somewhere. Okay. So can we now try to look at well, let's just run this for a second again. So this is showing me like the real answer on this guy. And I want to see what the predicted answer is. So we need to do this shit again down here. And then just huck a bunch of like val on everything that says layer here. except for the parts where we're actually doing the execution. Okay. Then we need to get these things back on CPU. Something like this. Like this. Okay, and then can we look at this is running on the wrong thing. Okay. But this thing needs to be in the tracing executor. Yeah, so validation reshaped traced is going to be tracing executor append node of validation reshaped doesn't initialize really like an entry point on the graph. Okay. And so now does this start to look like something? Okay, here we go. So this number is not really changing, right? It's kind of the same all the time. Are you just learning how neural network works? By some metric. I mean, we're trying to like make one ourselves, right? So I think saying that we're just learning how it works is like a little bit not quite there. Oh, his final output here, we're looking at like the sigmoid output. Because our like layer, first of all, we should be sigmoiding between our convolutional layers. Or at least doing some sort of like activation. So the fact that we're not doing that is fucking stupid. So can we do like sigmoid on here? And then can we just bypass that sigmoid on the final output? Just for now. No activation. Let's do this. Okay, let's try that. So here, when we do this final layer execution, we go to execute no activation. And let's see if those numbers look a little bit more interesting to us. Okay. Hype. And can we look at like the gradients? I would like to look at the gradient for how do I say this? I would like to look at like if at least the gradients for the validation, like the results, are pointing in the right direction. LR is too small. Yeah, it does kind of feel like that, right? Huh? Just up it by a couple orders of magnitude. Okay, that number is going down, which is good. Can we visualize? I want to visualize this result here. So can we do like val result CPU? Len is this. Okay. So we do a little Pythagoras, and then we do can we do like the image view set predicted to val result CPU 0 over len, val result CPU 1 over len? Okay. Okay, that should do something. We should be able to see like a green, like a blue line on this. Okay, so here we're seeing the blue line point directly up. Right, it'll be interesting to see if this thing like starts working towards like lining up with the red line as this loss number goes down. Because the loss number is going down. Really, it looks like it's not really fucking moving. Right? But maybe, I mean, we should this number is decreasing, which is cool. Right? So maybe we give it a little bit of time and see what happens. Maybe our batch size can go up again. But or we can start trying to diagnose. Like, it might be interesting to look at like more samples, right? Maybe this is a bad example to look at. Put your mouse on it and see if it's moving. Ugh. If it's moving very slowly. I suspect that it's like actually like inching towards like getting to a magnitude of 1, right? But again, like we do see this number decreasing. That's good, which means that it's learning something. What do we do here? It'd be nice if we could visualize like more of these. And like maybe it would be interesting also if we could like color like how wrong it is relative to the length that it's supposed to be, right? Like maybe it's spending all of its time right now just learning to normalize the number instead of like trying to learn anything of like significance. Okay, this is taking a long time. I don't know if it's just going to take a long time or if we can kind of like make it go a little faster. What if we like number of images up? You know? Oopsies. Oh, and then also, yeah, maybe doing some release building also might be interesting as well. We created the meme. What's the meme? He's got to work hard to do this shit. Oh, this is funny. A lot of this time is now being spent. These batch sizes are so large that like the GUI is freezing in between them. It's like 1 Mississippi, 2 Mississippi, 1 Mississippi, 2 Mississippi. Um, okay, here's what I think we do. Do we just let it run for a little bit? Is that the play? And YouTube video gets like accelerated here or something? Because I don't really know what else. I think that this might just take time, you know? So, I mean, it also could, like, which is a bad sign, by the way. It means that, like, our, it could be that our thing is, like, incredibly slow, right? That's, like, a very real possibility. So maybe we have to fix that. I would also like to try, can we initialize this thing in a way where it ends up pointing not towards 0, like 0, 0 initially? You know, I would like to like, or maybe pick a validation image where the, like pick a seed where the validation image is like a little farther away. Tiny batch size and many iterations are good too. Yeah, maybe we do that. Yeah, okay, so let's do this. Let's do this. Oh, we're also not randomizing our... We should randomize these as well. We should be... Let's start these with initial. Let's do this. Let's do this. Let's do this. You know, just in case. Brand source a few places. And then, yeah, I'm okay with also trying lower batch size. And then just kind of like increase learning rate to see if it like we can like get somewhat close. What's he pissed about? Oh, scratch here is the wrong. Okay. Okay, this is a more interesting one. Oh, we nanned. Learning rate too high. Let's go one layer down. I don't think that much time is being spent on CPU here, so I'm just going to keep doing debug builds. I think it's all GPU. Oh! 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 Oh, motherfucker! Look at that shit! That was... Okay. Okay. Let's see if it gets closer. Maybe he's like stabilizing around 0, which might be bad. That might indicate a bug. But we did see him fucking move. That was kind of hype. I mean, he might also be getting stuck. The loss is no longer going down anymore. Might be stuck in local minima. Yeah, true. But I think higher learning rate was bad. Okay. So I guess the question is, what is he doing here? He is right now his like did I reduce learning rate right there or increase it? I actually don't remember. Oh wait, let's take a look. He slowly. Oh, that's funny. If I scroll by mistake, it like fucks up the image. I probably reduced learning rate there, thinking that like it would approach cleaner. So yeah, I wonder if it is just learning to set the rotation to 0. Like, but like, what am I saying here? What am I trying to show? Like, here he's just kind of like approaching x to 0. But x should eventually get to go negative. Eventually. Increase learning rate. Well, I wanted to see if it was like failing to jump over some hump at around the 600 mark. So we could see if it like I'm kind of curious like why is it getting stuck pointing always up here? And like I'm also curious if it's always pointing up for all pictures or if it's like just for mine. Sigmoid can't go negative, no? Yeah, but shouldn't that be fine as long as my final layer doesn't have sigmoid on it? Right, like here we are doing no activation on the last layer. Which I would think should allow for that to work. But maybe not. Layer 5 Execute no activation. This thing does no sigmoid. What activation do you use for the conv layers? I think we're also just sigmoiding those as well. Yeah, the idea that it can't go negative is kind of interesting. Can we, who's using Rand right now? I wonder if we can do something like allow our initial weights to be negative as well. Hmm. Okay, let's just try a stupid thing. I just want to see with like a higher learning rate, is it like getting stuck there? I mean, we do see it. Oh, too high. So is the idea of not sigmoiding the final output also kind of fucking stupid? It might be. No, okay, he is tipping past like the straight vertical. Like he can go over there. It's possible for him. Okay, you know what? I think that sitting here and staring at this, however much I would love to get like a correct answer, is a bad way to spend like on-stream video time. So I think I'm gonna let this run for a little bit. Update you guys on YouTube for if it's working or not, or like what like tweaks I want to make, and I'll just like think about it, you know, in the background. Because I have to figure out where I think this problem is. Like we at the very least I should be coming up with like strategies on how to debug this better, and so I think that's just gonna need to take some time. But cool, we have something that is doing something. Ooh, Reddit meme watching a train model. Yeah, it is. Right, yeah. All right, cool. Thanks for watching, guys. I hope you enjoyed. If you like what you saw, we stream most days. We aim for 12:30 Pacific time to something else. 3 or 4 Pacific time. It is 3:50 now, so anywhere between 2.5 hours ago or 3.5 hours ago till now, I guess, when you should expect to see us. There's a bunch of stuff goes up on the YouTube, which is linked in the Twitch description. Some stuff does not. It's kind of like based off of if I think it's algorithm friendly or not. So take a look there. If you want to support the stream, there's a Patreon. You can use your Twitch Primes. You can become a YouTube member. Any of those are fair game. And in return, you get the stuff that the VODs that I think are not algorithm friendly. So if you want to support and help the stream stay alive, please consider, but obviously no pressure. Otherwise, I think that's it. YouTube, peace out, and Twitch, let's find someone to raid.